Welcome everyone. Today we are diving into the Continuous Ambient Air Quality Monitoring Station, or CAQMS for short. This system helps us understand how we monitor air quality using the latest instruments. We'll talk about what CAQMS includes, how we choose the right instruments, and some important technical details. This toolkit has been developed by IIT Kanpur with support from several organizations, including the Clean Air Project in India, the Energy and Resource Institute TERI, and the Swiss Agency for Development and Cooperation SDC. Next, let's look at air pollution. It's essential to know how pollutants like smoke and dust move from their sources like factories and burning waste through the air to reach us and our environment. Factors like wind and weather play a big role in this journey. As you can see in the image, these pollutants can affect people, plants, and even bodies of water. Here, we have the different units to measure pollutants and how we convert them. For example, we might look at how to convert part per million to micrograms per cubic meter. This helps us understand the concentration of pollutants in the air. Now, let's talk about why continuous air quality monitoring is crucial. It helps to ensure that factories and power plants follow government rules about emissions. We can use CAQM system for several reasons. Finding pollution sources. CAQM can track various pollutants like sulfur dioxide and ozone, helping us pinpoint where pollution comes from and how to manage it. It helps to improve air quality. By identifying areas with poor air quality, we can take steps to improve it. It helps to evaluate programs. We can actually check how well our pollution control programs are working. It also helps in creating new programs. If we find gaps, we can develop new strategies to address them. And lastly, it provides data. CAQM system can share real-time data with authorities, helping them take actions quickly. Let's understand the design of the CAQM station. Understanding the outer design. The housing for the CAQMS is crucial because it protects the equipment from dust, temperature changes, and other harsh conditions. The walls should have good insulation, at least R19 grade, to keep the inside temperature stable. It has two rooms, one the equipment room and the other is the data acquisition system room. We need to keep the internal temperature stable between 20 to 30 degree with minimal variation and maintain humidity level between 30 to 45%. This ensures the equipment works properly. Next, let's talk about earthing, which is very important for safety. It provides a safe path for electrical current to go into the ground if there is a problem, reducing the risk of fire. We need to install earthing systems in both the rooms, placed in opposite corners to prevent any electrical issue. It's also important to understand the soil conditions to choose the best type of earthing. The traditional earthing method uses a mixture of salt and charcoal. This system needs a specific installation space and regular maintenance, like adding more salt and charcoal every 3 months. Unfortunately, it can corrode quickly and may only last less than 10 years. Now, let's discuss chemical earthing, which is often a better option. It uses a copper rod surrounded by special materials that helps to reduce soil resistance. Some benefits of chemical earthing includes 1. It needs less space. 2nd, it requires less maintenance since you don't have to keep adding water. And 3rd, it lasts longer, about 10 to 15 years compared to traditional methods. We need to ensure that the top cast iron cover of the system is built correctly as shown in the image. This is vital for the safety and durability of the CAQM station. Let's look at the layout of our continuous ambient air quality monitoring system. It has two main parts, the equipment room and the data acquisition system, or DAS. In the equipment room, we have an instrument rack. It's really important that this area is free from vibration to get accurate measurements. There is an air conditioning unit to keep everything at a stable temperature. To make sure the instruments work well, we have installed a temperature and a humidity sensor to monitor these conditions. The DAS part includes the data acquisition system, a modem, a printer, and a backup power supply that helps to keep everything running if there is a power outage. There's also a stabilizer to prevent power fluctuations, and we have made sure everything is safely earthed for electrical safety. Cable conduits helps to keep the wiring organized. Plus, there are stairs leading to the room for easy access. Overall, this layout helps us function well and ensures we get accurate real-time air quality data. Depending on our needs, we can install a solar power system along with the UPS. For example, we could set up solar panels to provide energy for our monitoring system, make it more sustainable and reducing reliance on the grid. A typical example is given in the picture. When it comes to the electrical system, we need to use copper wiring that can handle both current and future loads. It's also crucial to have an emergency power shutdown system to ensure safety. Additionally, we will install a surge arrestor to protect our equipment from power fluctuations. It's important that all the cables are properly marked and organized. This makes the maintenance much easier and safety at priority as shown in the figure. Here's a schematic diagram of our air quality monitoring system. It starts with an air inlet where we collect ambient air. This air is then analyzed for different types of particulate matter like PM10 and 2.5. We have various gas analyzers that measure pollutants such as sulfur dioxide, nitrogen oxides, ammonia, carbon monoxides, etc. To ensure accuracy, we also have multi-gas calibration system in place. We have mounted meteorological sensor on a mast to track weather conditions like temperature, humidity and wind patterns. A computer at the station collects all this data and sends to a central computer for real-time monitoring and analysis. This system is essential for tracking air pollution and helping with environmental research and regulatory compliance. Now, let's discuss the key meteorological parameters we need to measure. These include ambient air temperature, humidity, wind direction, and wind speed. Understanding these factors helps to learn how pollutants move in the atmosphere. For the meteorological mast, we want it to be between 10 to 20 meters tall when extended and about 2 meters when retracted. We'll use 4 sections made from strong aluminium to ensure it withstands outer conditions. Let's talk about the sensors we need for accurate meteorological data. We should include anemometer to measure wind speed and direction, and one set of solar radiation, pressure, temperature, and precipitation sensors. Each of these sensors provide important atmospheric data. To protect our equipment, we'll incorporate lightning protection and anti-falling device into the tower design. It's also crucial to place the towers in open, flat areas where there are no obstructions to ensure accurate measurement. Here, we have a table that outlines our meteorological measurement quality objectives, detailing the key parameters for monitoring environmental conditions. For ambient temperature, we'll use a thermistor with a range of -30 to 50 degrees Celsius and a resolution of 0.5 degrees Celsius. Relative humidity will be measured with the hygrometer covering 0 to 100% with a resolution of 1%. Wind speed will be measured with an anemometer ranging from 0.5 to 50 meter per second with a resolution of 0.2 meter per second. Wind direction will be monitored using a vane covering 0 to 360 degree with a 1 degree resolution. We'll sample each parameter every hour and collect raw data every minute, ensuring we capture at least 75% of the data for reliable assessment. This table outlines our methods for verifying and calibrating our measurements to ensure accuracy. First, for ambient temperature, we will use a 3-point water bath to calibrate with an acceptance of 1 degree, checking annually. Second, relative humidity will be calibrated with NIST traceable standards, ensuring an accuracy of 10% RH, also verified yearly. Third, wind speed will be calibrated using a synchronous motor with an acceptance of 0.25 meter per second or 5%. Lastly, wind direction will be verified using methods like solar noon or GPS with a 5 degree acceptance for both calibration and accuracy. Each parameter will undergo annual verification to ensure we are collecting precise meteorological data. This slide explains how we check if an analyzer meets the standards set by the government. This process is important for all types of analyzers. we look at how well the analyzer performs, how accurate it is, and if it gives consistent results. By following this procedure, we can confirm that the analyzer is good for monitoring and reporting air quality. Particulate matter can be measured by the three methods given here. This slide shows the technique used by the US EPA for collecting particulate matter. Key parts of a PM analyzer includes an inlet for sampling the air, a fractionator that removes large particles so we can focus on smaller ones, an impactor that separates very fine particles. You can also see a very sharp cut cyclone VSCC, which helps us to collect the fine particles more accurately. The typical flow rate for the EPA inlet is 16.7 liters per minute, making sure we get reliable results. The image here shows a head design for official air quality monitoring. Now let's look at the European technique EN 12341 for collecting PM. This slide highlights special inlets that help to separate PM10 and 2.5. These inlets work well by having different sizes inside them to help sort the particles accurately. For the EN inlet, the typical flow rate is 2.3 cubic meters per hour or 38.3 liters per minute, which helps us get consistent and reliable measurements that meet European standards. It's crucial to keep the analyzer inlets clean and properly greased. This ensures they work smoothly and helps to prevent any blockages or damage. This maintenance is vital for getting accurate measurements. The principle behind beta attenuation particle sampling instrument beta gauge is that energy is absorbed from a beta particle as they pass through particulate matter collected on a filter tape. The attenuation due to only the measurable fraction of PM10 or 2.5. The difference between the baseline beta count and the beta count after sampling is directly proportional to the mass of PM in the sample. In this method, particulate matter goes through a nozzle that sorts PM10 and 2.5 and then it interacts with beta rays. The way the beta rays attenuates helps us figure out how much PM there is. The sample air is drawn through a size-selective inlet such as PM2.5 sharp cut cyclone at a controlled flow rate, and the relevant PM fraction is collected on a filter paper or filter tape. The diagram illustrates the quality control procedures necessary to maintain the accuracy and reliability of particulate matter measuring instruments. It highlights key checks such as flow rate, ensuring consistent air sampling, temperature, pressure, and relative humidity. Monitoring for environmental accuracy. Zero check, verifying baseline stability. Leak check, detecting any system leaks, and calibration, aligning instrument readings with known standards. These procedures are essential for data integrity in air quality monitoring. This table shows the acceptable tolerance levels for PM instruments, organized by how often we verify them and what we check. We have two types of PM instruments, continuous PM 2.5 and integrated PM. The verification process includes specific things we need to check, like flow rate, temperature, along with their acceptable limits. Keeping these tolerance level in check is essential for ensuring our air quality monitoring is accurate and reliable. Now let's talk about what are the probes we use to measure gases in the air. It's important to use the right material for these probes, depending on what gas we are monitoring. For acidic gases like sulfur dioxide and nitrogen dioxide, we prefer using borosilicate glass or Teflon. This helps to prevent any unwanted reactions. When checking carbon monoxide and ozone, we also typically use borosilicate glass or stainless steel. For volatile organic compounds, stainless steel or a special type of silicon-treated stainless steel is recommended. This choice helps to reduce any unwanted absorption and makes our measurement more accurate. The probes connect to something called an octopus manifold, which helps distribute air samples to the analyzer. Before we analyze the samples, we also use a moisture trap connected with Teflon to get rid of any water vapor. Let's take a quick look at a typical octopus-style manifold from top to bottom. At the top, we have the knurl connector, which ensures a secure connection. Below that, the O-ring seals the connection to prevent leaks. Next is the threaded opening where other components can be attached. The top extension is 56 mm long, providing space for further attachments. The overall length of the manifold is 304 mm. Its outside diameter is 24 mm. The top and bottom shoulders are 50 mm each, giving the manifold stability. The inlet tube is 30 mm long for sample entry. The distance between the inlet tube is 16 mm. The internal tube is 145 mm long, ensuring proper flow. The inlet tube's outer diameter is 6 mm. The distance from the inner tube to the wall is 18 mm. The inside width of the outer tube is 60 mm. The down tube is 76 mm long. The outer diameter of the down tube is 24 mm. The overall width of the manifold is 124 mm. Now let's talk about residence time or RT. This is the time it takes for a sample of air to travel from the probe to the analyzer. For monitors that check reactive gases, we want this time to be less than 20 seconds. To calculate the residence time, we need to first figure out the total volume of all parts in the system, including probe, sampler, and tubes. Then we find out about the overall flow rate, which tells us how quickly air flows from the system. Finally, we can use this formula given in the image. This calculation helps us to understand how well the system is performing. Now let's understand the maintenance of the manifold. The first thing is the leak test. The maintenance must be disassembled periodically and cleaned with the distilled water. Soap, alcohol, or other products that may contain hydrocarbons should be avoided when cleaning the sampling train. Plug the ports on the manifold when sampling lines are detached. Maintain a flow rate of the manifold that is either 3 to 5 times of the total sampling requirement or at a rate equal to the total sampling requirement plus 140 liters per minute. Now understanding the placement. Positioning air conditioning vents away from the manifold to reduce condensation of water vapor. Positioning air conditioned vents very away from analyzers. Install heat coils which wrap the manifolds and instrument lines to avoid moisture problem, and the manifold should have a moisture trap. While installing the probe, it's important to choose it carefully and place it away from any electrical source to avoid interference. Make sure it's properly connected to both the dehumidifier and the denoder. This helps to maintain accurate sampling and prevents moisture or contaminants from affecting the results. Also, do not forget to keep everything clean. Standardized reference methods are crucial for measuring air pollutants accurately. Here's how we detect some of the key gases. Sulfur dioxide, we use ultraviolet fluorescence. Nitric oxide, nitrogen dioxide, and total nitrogen oxides are measured by gas phase chemoluminescence. Carbon monoxide is monitored using non-dispersive infrared spectrometry. Ozone detection uses ultraviolet photometry. For volatile organic compounds like benzene, toluene, and xylene, we use gas chromatography. This diagram shows how the analyzer works step by step. It starts with the excitation of SO2 molecules by UV light, which then emits a special type of radiation. We have components like UV light source, a beam splitter, a photodiode, a multiplier, a phototube, and an electronic signal processor. These parts helps us to capture and process the light and data as they flow through the system. Here's a flow diagram that outlines the steps for calibrating an SO2 analyzer. It's important to remember that if we notice a zero shift or more than 15%, we need to recalibrate the system. This diagram illustrates how gases flow and how catalyst works in ambient oxides of nitrogen analyzer. First, NO2 is converted to NO, which alongside pre-existing NO is oxidized by ozone to excited state of NO2, which comes to ground state emitting luminescence, which is measured as NO. The switching valve in second stage allows NO for measurement. The difference in two analyses gives level of NO2. This gives us a complete overview of the analytical method for NO, NO2, and NOx. When it comes to detecting carbon monoxide, we use non-dispersive infrared spectrometry. The CO analyzer uses infrared light source to measure the CO concentration. The sample gas passes through the gas cell. The infrared radiation passes through the gas cell and absorbed infrared intensity is measured by the detector to infer the CO concentration. Now let's come to ozone. The commonly used method is UV photometry. The ultraviolet absorption method works on the principle that ozone absorbs ultraviolet rays in the area of 254 nanometer. Measurements are taken from continuous alternated injections of sample gas and the reference gas into the measurement cell. The UV absorption measure per detector to quantify the concentration of ozone. Continuous monitoring of ammonia concentration. An oxidation catalyst converts ammonia into nitrogen oxides and detection method is used to quantify the increased nitrogen oxides, the concentration as a measure of ammonia. Gas chromatography is used to detect organic gases like benzene, toluene, and xylene. In this method, the sample gas passes through a capillary column having a coating of absorbing material where organic gases molecules absorb on the surface of the gas as pass through the column. The column is heated at a constant rate inside the GC oven and the specific gas molecules deabsorbs from the column surface at a temperature and mix with carrier gas at a given detention time and reach the detector. The same type of molecule group together, allowing us to detect and identify each compound in the sample and quantify the concentration of organic compounds. When placing calibration gas cylinders, it's important to mount them securely in a well-ventilated area. Keep them away from heat and direct sunlight to avoid pressure buildup. The setup should include brackets at 2 levels for at least 6 cylinders, making it easy to access and maintain them. Each cylinder must be traceable to a standard organization for accuracy and contain synthetic air and nitrogen at 99% purity. We also need to make sure that gases like SO2, NOx, CO, NH3, benzene and toluene go through a dehumidifier and denoider first. This removes any moisture or contaminants before we mix them with an inert gas for calibration. The multi-point gas calibration system is designed to ensure our gas analyzers are calibrated accurately. It has a high-performance zero-air generator that produces ultra-pure air free from contaminants. This system also includes an ozone generator for precise gas phase titration and a special 2-chamber system that can accept primation tubes for flexible calibration options. Now let's discuss the primation tube. This tube helps us achieve very low concentration of calibration gas. We keep the calibration gas inside the tube under stable temperature and pressure. Then we pass zero air or inert gas through it, allowing a small amount of calibration gas of known concentration to mix in for use. This slide shows the calibration ranges for gas analyzer. We have 2 tables here. The first lists the calibration ranges for pollutants like sulfur dioxide, nitrogen oxides, carbon monoxide and ozone in parts per billion or million. The second table outlines the tolerance level for the quality control checks, which includes limits for zero and span checks for these pollutants. Using traceable standards for multi-point verification is crucial. It helps to check the accuracy of our instruments regularly and ensures our data is valid. This process involves pre-zero or post-zero checks and include at least 3 test points at different levels of the calibration stage. In this graph, the x-axis shows local standard time while the y displays the analyzer's response. The blue line shows how the analyzer responds over the time, with plateaus and drops corresponding to the calibration points and zero levels. The zero check involves introducing clean air to see how analyzer reacts at very low concentrations. We compare this response to a previously established zero figure. If the zero value is not within tolerance level, we need to adjust it using a scrubber or zero air source. Also, if the zero check value is not close to zero, after our multi-point verification, we may need to replace the scrubber's media. For the span check, we introduce a known concentration of pollutant gas that is higher than what we usually expect. Then compare this result to a reference value established during our earlier checks. If it's outside the acceptable range, we perform another multi-point verification and take necessary actions to ensure everything is accurate. Coming to data verification, this step is super important to make sure each piece of data we collect is accurate. We mark data points as either valid or invalid using special codes. For things like extreme outliers, we have 4 levels of verification. Level 0 is where we do automated and manual checks to flag any data points that look suspicious. Level 1 is more detailed. Look at all the data level from 0, including checking records from the field and results from our test. This helps us to make sure the data is reliable. This slide focuses on how we check the accuracy of gas analyzers. If the readings drift outside of the acceptable range, we need to correct it and check if the instrument is working properly, like checking the pump flow or scrubber. All the typical parameter settings are mentioned in this slide. In the chemiluminescent analyzers, we don't measure NO2 directly. Instead, we find it by subtracting the amount of NO from the total NOx. If we make any changes to NO or NOx, we have to adjust NO2 too. This keeps everything in balance. For certain analyzers, we allow a small difference in the NOx value to ensure we are getting accurate readings. Level 2 validation is where we take another careful look at data to ensure any issues from level 1 are fixed. We do this every 6 to 12 months, reviewing data from the past few months. We compare data from the same site and nearby sites to make sure everything adds up. All of this is explained in the graph. Level 3 validation is about having someone independent review the validated data. This person should not be involved in the previous checks to ensure a fresh perspective. They should know a lot about air pollution and weather patterns to assess if the data behaves as expected. In this slide, some performance parameters are mentioned. For example, cell temperature, high voltage, cell pressure, etc. As shown in the slide, the sensor data is transmitted to a computer, server, or cloud facility for storage. From there, the data can be broadcasted via the internet, allowing users to access it remotely for analyzing and monitoring, and then visualize the AQI. The data acquisition frequency can be set as required, ranging from 1 to 120 seconds. The system should be expandable, capable of accommodating up to 64 sensors or instrument data lines in the future. Additionally, an onboard or on-air control data acquisition facility should be incorporated for efficient operation. For the data storage, the ISO 7168 format protocol is used with a double data entry to ensure data integrity for at least 2 years. The data must be stored in binary or encrypted format for security and confidentiality, and this information should be communicated to relevant authorities for compliance and monitoring purposes. When moving data from our computers to the server, we need to make sure it's done safely and is only accessible to the authorized users. We also have to make sure a backup process to keep data safe and should regularly check our system to catch any problems very early. When we work with the data, we need to understand how to summarize it efficiently. One way to do this is by looking at something called central tendency, basically where most of our data points are centered. There are 3 ways to measure this. First is mean or average. This is the most commonly used measure. We calculate by adding up all the value and dividing by total number of data points. It gives us a general idea of dataset but can be influenced by extreme values. The second one is median. This is a middle value when we arrange all the data points in order. If there is an even number of values, we take the average of the 2 middle ones. The median is useful when there are outliers, as it isn't affected by extreme values. The third one is mode. This is the number that appears most often in a dataset. It helps to identify common trends and is useful for analyzing data categories like the most popular product in a store. If our data is normally distributed, which means it has a symmetrical bell curve, all 3, mean, median, and mode are about the same. But if our data is skewed, leaning more towards one side, they may be quite different. That's why looking at 3 measures helps us to understand the data. Coefficient of variation (CV) measures how much variation exists in relation to the average value. It's calculated by dividing the standard deviation by the mean. The lower the CV means data is more consistent. If CV is below 0.5, the data is likely well behaved. Correlation coefficient measures how strongly two variables are related in a straight line pattern. If the correlation is close to 1, the datasets have a strong linear relationship. They increase or decrease together. If the correlation is 0, there is no linear relationship between them. Correlation analysis helps us to see two different things. +1 means strong positive correlation. They both increase together. 0 means no correlation, completely unrelated. And -1 means strong negative correlation. One goes up, the other goes down. For example, if CO and NO2 have a high correlation, they're likely to come with the same pollution source. Moving averages help smooth out short-term fluctuations in data, making long-term trends more visible. This is done by calculating the average over a set period, like a week or a month. In air pollution studies, moving averages can reveal seasonal patterns such as higher pollution levels in winters and lower in summers. Trend analysis identifies long-term patterns in data. In air quality studies, pollutants concentration are plotted over time, and polynomial regression models help detect trends. If all coefficients A, B, and C are positive, the trend shows a steady increase over time. If A is positive, but B and C are negative, the trend rises first and then declines. If observed and estimated concentrations have a strong correlation, the trend analysis is considered meaningful. Trend analysis helps to evaluate the effectiveness of environmental policies. If no clear trend emerges, it may indicate that intervention have had little impact or that other factors are at play. In the first plot, we see the trend over time, where the Y is representing the concentration and T is time or specific day of collection data. The R2 value indicates a strong correlation even with limited data points. All three regression coefficients A, B, and C are positive, showing an overall increasing trend. In the plot B, we analyze the relationship between pollutant concentration Y and time T. Here, the regression coefficients indicate A, which is constant, is positive, showing a general increase. B is negative, suggesting an initial decrease in concentration. C is positive, indicating a later rise in concentration. This pattern aligns with the dataset where pollution level initially drops before increasing. Correlation analysis helps in understanding the linear relationship between pollutants across different time intervals. In this analysis, we examine the correlation between PM10, TSP, total suspended particulates, and NO2 over 3 time slots. 1. 6 am to 2 pm, second 2 pm to 10 pm, and the last 10 pm to 6 am. For example, the correlation between PM10 and TSP from 6 am to 2 pm is 0.78, indicating a strong relationship means that PM10 is largely a data subset of TSP. Similarly, PM10 also shows strong correlation with NO2 across different time intervals, suggesting that both pollutants likely originate from common combustion sources such as vehicle emission or industrial activities. Next, we look at key weather factors that affect how pollutant spreads. First, wind speed. Higher wind speeds help disperse pollutants, reducing their concentration in one area. But when wind speed drops below 0.5 meter per second, air becomes stagnant, causing pollutants to build up. Second, wind direction. This tells us where pollutants are going. We measure it in degrees, where 0 degree being north, moving clockwise. For instance, if wind is blowing from 270 degrees west, it is moving towards east, impacting areas down of the wind source. To visualize wind data, we use wind roses, which shows wind speed and direction over time, divided into 16 categories like north and northeast. Here's what we found. Wind blows from northwest about 10% of the time, making it most common direction. The least frequent winds come from the south and southwest around 4% of the time. The strongest winds typically come from west-northwest and north-northwest. Calm conditions where wind speeds are below 0.5 meter per second happens only 0.5% of the times, leading to poor dispersion of pollutants. Understanding these weather influences is crucial for modeling air pollution and figuring out where it comes from, helping us to plan effectively. A typical instrument procurement acceptance should include factors such as compliance with local environmental conditions and government requirements. This ensures that the instrument meets regular standards and can be procured and operated accordingly. The acceptance process should cover all aspects of calibration, functionality, accuracy, and adherence to required specifications to ensure the instrument proper use in the field. Every time we calibrate an instrument, we should keep a checklist. This should include standard use, results, adjustments made, and who did the calibration to ensure we have a good record. Finally, these checklists are mandatory for the operations and maintenance of continuous ambient air quality monitoring system to ensure everything runs smoothly. The team that has contributed to the successful implementation of this project are IIT Kanpur, the technical insight and guidance by Professor Mukesh Sharma, technical review by Dr. Pawan Kumar Nagar, contribution from Airshed Planning Professionals, framework and review from Dr. Dhiren Singh, research and presentation from Mr. Shekhar Agarwal, script development from Dr. Rajesh Singh, content narration and script development from Ms. Shreya C. Gandhi, project coordinator, Terry, Dr. Anju Goel.